Hello and welcome to this lesson on volume. I left you in the last lesson with a task to check what the effect of doubling dimensions on different right prisms was. If your measurements and calculations were accurate, you should have found what I found. If you double the dimensions of any right prism, you make its volume 8 times more. In this lesson, we want to take this idea further. What happens when you make the dimensions 3 times bigger or 4 times bigger? What happens if you halve the dimensions? If we see a pattern in all these investigations, we could even answer this question. What happens to the volume of a right prism when all its dimensions are multiplied by k? K stands for any constant number. By the end of this lesson, you should be able to investigate how changing the dimensions of a prism changes the volume of the prism, find a rule to describe the effect of multiplying the dimensions of a prism by k, and calculate the changed volumes of right prisms. Because I want to find a general rule, I will start with a really easy volume. That way we won't be distracted by the numbers involved. So here I have a single cube with a length of 1 unit. That means it has a volume of 1 times 1 times 1, which is 1 cubic unit. When I double its dimensions, I get 2 times 2 times 2, which gives me a cube with a volume of 8 cubic units. 8 is 8 times more than 1. This is what we have already seen in the last lesson. Now I'm going to continue the pattern to see what we get. This time I will multiply each dimension of the cube by 3. So this length is 3, so is this one, and so is this one. The volume will be 3 times 3 times 3, which gives me 27 cubic units. Interesting! This is huge! The volume of the new cube is 27 times bigger than the original volume. Let's put the findings that we have so far into a table. This helps us to look for a pattern. When you make a table, be very clear about what each row stands for. Our top row needs to be the lengths of the sides of the cube in units. The second row is the volume. If I say here in cubic units, I won't need to write that into each result I find. So our original cube had dimensions of 1 and a volume in cubic units of 1. When we doubled the dimensions to 2, the volume was 8, and when we made the dimensions 3 times bigger, we got a volume of 27. Let's test one more increase in the dimensions. If I make the length of the cube 4 times longer, then the volume will be 4 times 4 times 4, which is 64 cubic units. By now, you have probably recognized the pattern that we have here. Did you see that 8 is 2 cubed, 27 is 3 cubed, or 3 times 3 times 3, and 64 is 4 times 4 times 4, or 4 cubed. Can you predict what will happen if I multiply all the dimensions of the cube by k? The volume will be length times breadth times height, which is k times k times k. There we have it, k cubed. So far, we have only looked at multiplying the dimensions of a cube by a number bigger than 1. What happens if we halve the dimensions of the cube? How does this affect the volume of the cube? If we halve each of its side lengths, we get lengths of half a unit. So the volume will be half times half times half. That gives us a volume of 1/8. The new volume is 1/8 of the original volume. This is a useful finding. Did you realize that a half cubed is an eighth? So the pattern that we found earlier, the cubing pattern, also seems to apply when the dimensions are decreased or multiplied by a factor of a half. When k equals a half, k cubed equals a half times 3, which equals an eighth. Well, the pattern seems to be working well for cubes. As a class activity, you could work out what happens to a cube if you divide each of its lengths by 3. You should find that the new volume fits the rule that we have made. What this means is that you should find that the new volume is k cubed, but this time k is a third. But are cubes the only type of prism that we can use this formula for? What happens to other right prisms when you multiply its dimensions by k? Let's test another right prism. This time we will work with a right rectangular prism. Again, we will choose easy numbers to work with. Here is a prism with a length of 4 units, a breadth of 3 units, and a height of 2 units. The volume of this right prism will be the area of the base, which is 4 times 3 times the height of 2. So it has a volume of 24 cubic units. If we double each of these lengths, we get 8, 6, and 4. The volume of the new prism will be 8 times 6 times 4, and that comes to 192 cubic units. If our rule works, we should find that this volume is 8 times more than this volume. 192 divided by 24 equals 8. Great! This fits our rule. The k value of 2 was cubed to get 8. So the volume of 24 was multiplied by 2 cubed to give a new volume of 192 cubic units. Let's test the rule when we multiply the lengths of the sides by 3. This length will be 4 times 3. That's 12. This will be 9, and this side will be 6 units. Let's find the volume. That will be 12 times 9 times 6, which is 648 cubic units. 648 divided by the first volume of 24 is 27. Do you see the pattern that is coming through here? Let me write this pattern differently for you. When we doubled the dimensions, we multiplied the original volume, volume 1, by 2 cubed. When we multiplied the dimensions by 3, we multiplied volume 1 by 3 cubed. Let's check that this pattern works for one more value. Instead of choosing the next value in the pattern, which would be 4, I will choose a value that makes the volume smaller. Let's choose to divide each dimension by 3. So the length will be 4 all divided by 3. The breadth will be 3 all divided by 3, which is 1. And the height will be 2 all divided by 3. The volume will be 4 all divided by 3 times 1 times 2 all divided by 3. Multiply these together and you get 8 all divided by 9. If the rule we have been using is correct, then we should be able to say that 8 all divided by 9 is the same as 24 times 1/3 cubed. 1/3 cubed is 1 all over 27, so we get 24 over 27. If we divide the top and the bottom of this by 3, We get 8 all over 9. Wonderful! What we have done here confirms our rule yet again. We have found that if you multiply all the dimensions of this right rectangular prism by some number, then the volume of the prism will be multiplied by the cube of that number. That was a mouthful. Let me say it this way. Let K be a constant number. If we have a prism with a volume of 24 cubic units and we multiply the dimensions of the prism by K, then the volume will be multiplied by K cubed. You need to try this out on another rectangular prism for yourself. Choose one that has a different volume from the one we used here. Now let me explain this to you using algebra. We can say that the volume of any right rectangular prism can be found using volume equals area of base times height. The area of the base is length times breadth. So we get V equals L times B times H. If we double the dimensions, we will get 2L times 2B times 2H. That is 2 cubed times LBH, or 8 times LBH. So we have 8 times the volume when we multiplied each dimension by 2. If we multiplied each of the dimensions by 3, we would get 3L times 3B times 3H. That is 3 cubed times LBH, or 27 times LBH. So we have 27 times the volume when we multiplied each dimension by 3. If our pattern that we have set up here is correct, surely we can use it to find an algebraic formula for calculating the new volume if the dimensions of a prism are multiplied by K. We will get K times L times K times B times K times H. That is the same as K cubed times LBH. So the new volume will be K cubed times the original volume. So far, our investigation has been limited to a cube and a right rectangular prism. However, if you test this idea on triangular prisms, on cylinders, even on hexagonal prisms or on trapezoidal prisms, you will find that this rule or generalization still applies. Here's your task for today. Here are a right cylinder and a right triangular prism. Test the following conjecture on them both using several different values for K. For any right prism, if you multiply its dimensions by K, the volume will be multiplied by K cubed. Use pi equal to 22 over 7 for the cylinder. Thank you for joining me in this interesting investigation. You need to keep making and testing your own conjectures about maths. You'll be amazed at what you find. From me, goodbye.